the previous lecture, we were discussing the effect of scaling of variables and scaling of the objective function value on the calculation of the gradient and Hessian of the objective function of an unconstrained optimization problem. Now, slowly we are going to jump on the discussion of optimization methods, optimization algorithms to find a local minimum point of a given objective function of several variables. Now, towards this computation of the consecutive iterative points to reach at a local minimum point of a given objective function, when we talk about optimization methods or optimization algorithms, obviously we are going to start our optimization algorithm from a given initial point, and then by following certain rules of the method you go for computing the consecutive iterative points, but keep on computing these iterative points till how far we go for computing these iterative points. Obviously we go for computing these iterative points unless a stopping criterion is met. Now question comes, what should be an appropriate or practical stopping criterion to stop this computation of the consecutive iterative points? In this lecture we endeavor to find a practical stopping criterion to stop an optimization algorithm to solve an unconstrained optimization problem. In finding a practical stopping criterion, we must take care about the following questions. That have we solved the problem so that we are stopping the algorithm, or have we ground to a halt so that we are not able to move further and hence we need to stop the algorithm. In this lecture, we will address these two questions, that have we solved the problem or have we ground to a halt. In finding the answer to the first question, that have we solved the problem, we note that we endeavor to identify a solution to the problem minimization of a function of several variables. And in finding a solution to this problem, we are employing an optimization algorithm which we usually refer as a descent algorithm. We see that any descent algorithm generates a sequence of iterative points xk. Now by these have we solved the problem, then we exactly mean, does this sequence xk converge to a local minimum? In order to guarantee convergence of xk, we note that we require limit k tends to infinity xk is equal to some point, say x bar, where x bar is a local minimum of the function f if not a global minimum. Here, as the function f is commonly assumed to be continuously differentiable, we notice that this limit xk is equal to x bar essentially imply limit k tends to infinity f xk is equal to f x bar. This is due to the continuity of the function f, and thus for convergence of xk we necessarily require that for a termination scalar or for a precision level or for a tolerance level, say epsilon greater than 0, we necessarily require that the absolute difference between fxk and fx bar is less than epsilon, or norm of xk minus x bar is less than epsilon after certain index number k. If either this or this condition is satisfied, then we can sense that the sequence xk is possibly converging to the point x bar, and hence we may go for stopping the algorithm. So you may think that this condition or this condition may possibly act as possible criteria of stopping an optimization algorithm. But unfortunately, none of these two conditions is practically applicable because we do not have information of x bar a priori to check these two conditions. So then from the practical perspective, to identify a solution to this question, that have we solved the problem, we need to then identify some other way out. Well, then we recall the results, the global convergence results that we have derived in one of the previous lectures. The global convergence of a general descent algorithm for exact line search or inexact line search, or we may also recall the lecture in which I was addressing that where do general descent methods converge. There we have found that almost always a general descent algorithm converges to a local minimum, or at least accumulating the last two lectures that the global convergence of general descent algorithm, where we have found that the sequence of iterates xk converges to a point at which the function f has a stationary point, and the last lecture where we have found that almost always a general descent algorithm converges to a local minimum. Accumulating these two results, we may at least settle with the final answer that a general descent algorithm majorly converges to a stationary point, obviously under certain mild conditions that are commonly satisfied by continuously differentiable functions. This stationary point is mostly a local minimum, and in case the algorithm approaches towards a saddle point, there are way outs to escape saddle points in polynomial time for a large class of objective functions. You please look at the references towards the end of the lecture, the last lecture. I have mentioned there are four references in which I was mentioning there are way outs to escape saddle points. Thus, the question, have we solved the problem by a general descent algorithm, can be broadly recasted just by have we reached to a stationary point. So we can go for employing a stopping criterion as that have we found a point xk at which we have gradient of f is equal to the null vector. However, practically the condition that this equality cannot be directly employed as a stopping criterion because numerical computation of gradient of fxk will rarely be identically zero. So a practical stopping criterion can be the norm of this gradient is less than a pre-specified threshold, say epsilon. This epsilon is commonly referred as termination scalar or the tolerance level or a precision scalar. So this condition may be a suitable condition which is also practically implementable as a stopping condition for a general descent algorithm. But a simple test like this one is inadequate since the gradient of f is strongly dependent on the scaling of both the function as well as the variable x. In the last lecture, I was trying to show that if we change the variable space from x to x hat, how the gradient gets changed. There we have found that this gradient will be changed with a pre-multiplication of the inverse of the transformation matrix, and if we scale up the objective function f by a constant c, then this gradient gets changed by that c multiplication of the gradient. So this gradient of fx as severely dependent on the scaling of the variables or the scaling of the objective function, a simple test like this is inadequate due to its inherent dependence on scaling. So a common remedy here is to use the relative gradient that takes care of scaling of both the objective function as well as of the variable x. A relative gradient of the function f is defined by, for relative gradient we use the notation nabla superscript r. This capital R stands for relative. The relative gradient of f at x is defined by the first component as g1 relative at x, second component as g2 relative at x, and the nth component is gn relative at the point x, where this gi relative at x is defined by, we notice that this gi relative is the ith component of this gradient, and this gradient is a replacement of the usual gradient of f, and in the gradient of f the ith component is the partial derivative of the function f with respect to the ith variable. This partial derivative of f with respect to the ith variable is defined by the limit delta tends to 0. In the numerator, how much the function value gets changed by the movement of xi, the ith variable, from xi to xi plus delta. So here in the numerator you will have the difference between fx plus delta ei minus fx divided by the change of the variable xi, that is given by xi plus delta minus xi. Now here in defining the relative of gi, that is the relative of this partial derivative, we consider limit delta tends to 0 of a ratio, where in the ratio we have in the numerator the relative change of the function value f due to the delta movement of the variable xi. Here in the numerator we had the change of f due to the delta movement of the variable xi, but here we have relative change of f due to the delta amount movement of the variable value of xi. And in the numerator we take relative change of the variable xi due to the delta movement of the variable xi. And now we compute this limit, that limit delta tends to 0. In the numerator you will have the relative change of f, that is given by the change of the function value fx plus delta ei minus fx divided by the function value at x. In the numerator we will have the relative change of xi, that is given by xi plus delta minus xi divided by xi. Here this ei is the ith unit vector in the standard basis of Rn. Now we go for calculating this limit. This limit is given by limit delta tends to 0. We have a constant factor xi divided by fx. This term is not dependent on delta, multiplied with fx plus delta ei minus fx divided by delta. So finally this GIR is given by xi divided by fx times this limit delta tends to 0 of this quantity, which is the partial derivative of the function f with respect to xi at the point x. Now you compute this gi relative for every possible I is equal to 1, 2 till n, and you will get this relative gradient of the function f, and we can go for employing the stopping condition as norm of the relative gradient of the function f at the point xk is less than epsilon. And when we employ this stopping condition, then we note that this condition is not dependent on the scaling of the variables or on the scaling of the objective function f. So we can just simply go for employing this stopping condition to terminate an optimization algorithm to solve a minimization problem. However, there is a bit drawback of this stopping condition, that while calculating the relative change of the function and of the variable xi, we took off the division with this function value fx and with this xi. These two quantities will break down if this fx is very close to 0 or this xi is very close to 0. To fix this problem, what we do? We replace this xi by a non-zero quantity given by maximum of modulus of xi and a typical magnitude Tm of the value of xi. And also this fx is replaced by maximum of absolute value of fx and a typical magnitude of the function value at x. Here this abbreviation Tm stands for typical magnitude, that represent user's estimate of a typical magnitude of the function value f. Similarly, here in this typical magnitude of xi, it represents user's estimate of a typical magnitude of the value of xi. This typical magnitude of a number, say xi, is a representative value of the range of absolute value of xi. This typical magnitude of a variable, say xi, a real valued variable xi, must be so chosen that it reflects a sense of scaling factor in the values of xi. Commonly, the midpoint or the points nearby the midpoint of the range of modulus of xi is chosen as a value of the typical magnitude of xi. Now, let me give you a few exemplary instances for typical magnitude of xi corresponding to the anticipated ranges of the variable xi. Let's suppose in the first column we will write anticipated range of the variable xi. Here in the second column, let us go for writing the range of xi, and finally a typical magnitude of the variable xi. In finding a typical magnitude of xi, I repeat here that this typical magnitude of xi has to be chosen so that it reflects a sense of the scaling factor or the range of the values of xi. So in finding a typical magnitude of xi, what we commonly employ is that you choose a typical magnitude of xi so that 1 by typical magnitude of xi times the range of absolute value of xi is near about the unit interval 0 to 1. You can even consider here, instead of unit interval, you can consider simply an interval of length around 1. So you can choose here the interval, say 0 to 0.9 or even 0 to 1.1, or maybe at max you can choose 0 to 2. Let me give here a few instances of choosing this typical magnitude. Let us suppose the anticipated range of xi is, say, in between minus 10 to the power 8 to 10 to the power 8. Then the range of absolute value of xi is 0 to 10 to the power 8, and then you go for taking the midpoint or around the midpoint of this range. That will give us a typical magnitude of xi. So here maybe half, or let's suppose 3 by 4 or whatsoever, around half times the length of this interval 10 to the power 8. If we anticipate the range of xi as minus 10 to the power 5 to say 10 to the power 10, then the range of absolute value of xi is 0 to 10 to the power 10, and hence a typical magnitude can be chosen as say 3 by 7 times 10 to the power 10. This typical magnitude is just a representative value. It is not a unique number. So instead of 3 by 7 here, you could choose half, 3 by 4, or some value around half, so that this equality is going to be valid. Let me give few more instances. So here, let's suppose the anticipated range of xi is minus 10 to the power 4 to minus 10 square. Then range of absolute value of xi is 10 to the power 2 to 10 to the power 4. A typical magnitude can be chosen as half times 10 to the power 4. If the range of xi is say minus 3 times 10 to the power minus 6 to till minus 6 times 10 to the power minus 7, then for a typical magnitude you can choose a number in between 6 and 30, so maybe a midpoint of 6 to 30, or simply let's suppose we are going to take 20, so 20 times 10 to the power minus 7, and that gives us 2 times 10 to the power minus 6. If the range of xi is 5 to 70, then a typical magnitude may be chosen as say 40, and for a range of let's suppose minus 5 to 70, a typical magnitude can again be chosen as 40. Keep in mind that in choosing the typical magnitude of xi, you consider a good representative of absolute value of xi in the sense that it captures the scale of xi. With this sense of typical magnitude, then a practical stopping condition can be this one, but this relative gradient has to be computed in taking care of this fxi and xi being replaced by these two quantities, which will ultimately reflect here in this factor xi divided by fx. So we replace here xi by this maximum of absolute value of xi times typical magnitude of xi, and similarly for fx you replace by this expression. Then you will get this gradient of the function fx with relative gradient and with a typical magnitude. So a practical stopping condition then can be the relative gradient with typical magnitude at the point xk has norm less than epsilon. So ultimately the resulting practical stopping condition is given by the norm of the relative gradient with typical magnitude. We write it as r comma tm of the function f at the point xk is less than epsilon, where this gradient relative with typical magnitude of f at xk is given by g1r with typical magnitude at x as the first component, the second component as g2 rtm at x, and the nth component is gn rtm at x, where the ith component of this relative typical magnitude, that is GIRTM at x, is given by xi divided by fx but with relative values. So here you take maximum of absolute value xi and typical magnitude of xi divided by maximum value of fx with typical magnitude of fx times the partial derivative of the function f with respect to xi at the general variable x. Notice that this quantity is independent of any change in the scale or unit of the function f as well as of the variable x. So this condition can be the most practical stopping condition for terminating an optimization algorithm to solve an unconstrained optimization problem. Now here I would like to put a very special comment about the common use of this typical magnitude of xi. We see that here in this expression on computing gi relative, we have replaced these two quantities fx and xi respectively by this and this for just one fact that we want to sidestep a possibility of dividing by a very small number. However, in common textbooks, you will find that these two quantities are commonly modified by the substitution for this quantity being replaced by just maximum of absolute value of xi and 1. Similarly, commonly this expression is modified by maximum of absolute value of fx and 1. Now, from the guideline to choose the typical magnitude that I have mentioned, it is then apparent that the substitution, this maximum of absolute value of fx and 1, or this maximum value of modulus of xi and 1, they make the implicit assumption that the values of xi has a scale around 1. Then only you can replace this typical magnitude by 1. But if we just go for deliberately replacing this quantity by maximum of absolute value of fx and 1, then this will work well only when mod fx is bigger than 1, and this will not at all be a good replacement if modulus of fx is much smaller than 1. A more severe substitution is just go with replacing this fx by simply 1 plus modulus of fx. But again you note that instead of using this maximum of modulus of fx and typical magnitude of fx, if we simply replace this fx by 1 plus absolute value of fx, then this replacement will work well only when modulus of fx is much greater than 1 and will not work well when modulus of fx is much smaller than 1. So we need to be careful while replacing this fx and xi by maximum of modulus fx and 1 or maximum of absolute value of xi and 1. Ideally, we have to replace this fx by maximum of modulus fx and typical magnitude of fx, and we ideally have to replace this xi by maximum of absolute value of xi and typical magnitude of xi. Commonly, these substitutions, maximum of absolute value of xi and 1 or this maximum value of absolute value of fx and y, are not suitable replacement. So accumulating all, the answer to this question that have we solved the problem is ideally reflected by the condition that we have derived, that you go for stopping the algorithm when you have this gradient relative with typical magnitude at fxk is less than epsilon. Now we would like to address the question that have we ground to a halt. Note that there can be two reasons for whether a descent algorithm has a ground to halt. The first is that the algorithm has converged. The second is that it has stalled. That means it is crawling around a point without making a substantial improvement of the variables or of the objective function values. So by halt equivalently, we can have two reasons. The first, for a ground to halt, the algorithm has either converged or it has stalled. By the phrase that algorithm has converged, we essentially mean one of the following three. That the first, the sequence generated by the algorithm, the sequence xk, has converged, or corresponding to the sequence xk, the sequence of real numbers, if xk has converged, or corresponding to the sequence xk, the sequence of vectors gradient of f xk has converged to the null vector. This part, when norm fxk is converging to 0, is already detailed in finding the answer to the question that have we solved the problem. Now then we shall look into these two particular cases for grounding to a halt. We notice that we can check whether this xk has converged by the condition that norm xk minus its limit is less than epsilon. But as we do not have any information for the limit of xk, we can check the convergence of the sequence xk by checking if the sequence xk is a Cauchy sequence, and essentially then we can go for checking this xk has convergent by checking if the consecutive terms of the sequence xk plus 1 and xk has distance substantially smaller. Similarly, for the second case, we go for checking whether f xk has converged by checking that f xk plus 1 minus f xk has absolute value less than epsilon. Here I would like to point out that a condition that this is less than epsilon does not essentially prove that fxk, this sequence, is convergent, but this is an essential condition or a necessary condition for convergence of fxk. Now next, for this phrase, the algorithm has stalled. By this we mean the following two, that either the sequence xk generated by the algorithm is generating a sequence of points for which the consecutive iterates are almost identical, that is the condition norm of xk plus 1 minus xk is less than epsilon, or we can also go for checking for the function value getting stalled, which is checked by whether the absolute value of fxk plus 1 minus fxk is less than epsilon. So after certain index number, say k greater than equals to k1, if this condition is going to be true, then the algorithm is getting stalled or not making any improvement of the generated points xk. And if this condition is true after certain index number, say k greater than equals to say k dash, that means the consecutive terms of fxk are almost the same. Then the algorithm is getting stalled due to the fact that it is generating a sequence xk for which the function values are not making any improvement. But here I would like to mention a point. You may think that this condition or this condition are equivalent, but not really so. That we cannot interchangeably use either this condition or this condition to mean that the algorithm has stalled or ground to a halt. I would like to give two examples showing that these two conditions are not equivalent. You consider the first example as you take the function fx, a function of one variable, given by say 1 upon x, and you consider the sequence of points xk's are given by say k for any natural number k. Now if we move along the sequence of points xk, then we see that we are actually moving along the descent direction of the function fx equals to 1 upon x, because at x1 we are at 1, at x2 we are at 2, at x3 we are at 3. Once we move from 1 to 2, 2 to 3 and so on, we are moving along these points, and these points are making subsequently degradation of the function value. So we can think that this sequence xk is a sequence of points generated by a descent algorithm. Now for this particular sequence xk, we note that we have f xk plus 1 minus fxk is equal to 1 over k times k plus 1, which is less than 1 by k, and hence this is less than epsilon for all index number k greater than equals to the value of k dash is equal to the greatest integer function of 1 over epsilon plus 1. So here we notice that these function values fxk's are not getting changed after the index number k dash. But even if these function values are not getting changed, we look at the difference of the sequential points xk plus 1 and xk. We see that this is identical to 1, which is not smaller than epsilon for any chosen epsilon that is less than 1, and therefore this condition is not equivalent of this condition. Now I would like to give an example where we'll see that this is satisfied but not this one. For such an example, we take say the expression of if x is equal to 1 over x minus 1, and you go for taking the sequence xk is equal to 1 minus 1 over k, where k is a natural number. Here also for this example you can check that in the graph of the function fx, the sequence of iterates xk's consecutively, they move along the descent direction of the function fx, and we have here that the absolute difference of xk plus 1 and xk is equal to 1 over k times k plus 1, which can be made lesser than arbitrarily small quantity epsilon after certain index number, say capital K, which is given by the greatest integer function of 1 by epsilon plus 1. But here you see that fxk plus 1 and fxk has absolute difference equal to 1, which is again not less than epsilon for any chosen epsilon that is less than 1. And therefore, these two conditions, that norm xk plus 1 minus xk less than epsilon and this absolute value of fxk plus 1 minus fxk less than epsilon, these two conditions are not equivalent. And accumulatedly, from this entire discussion, we see that have we ground to a halt essentially mean either these, by which we mean have we converged, or by these two conditions, by that we mean have we stalled. And we look at these two conditions and we see that they are identical, and hence have we ground to a halt essentially mean that is either of this condition or this condition is true. So we write neatly here that have we ground to a halt is equivalent of checking that either norm of xk plus 1 minus xk is less than a tolerance level epsilon, or by checking that if xk plus 1 minus fxk has absolute value less than epsilon. If either of these two conditions is true, then we can ensure that we have a ground to hold that either the sequence of iterates are not improving or the sequence of function values fxk's are not altering. So if either of these two conditions hold, then we must stop the descent algorithm which is employed to solve an unconstant optimization problem. Here, I would like to mention a very special note that if the graph or surface of the function fx nearby the point xk is flat, then the condition that absolute value of fxk plus 1 minus fxk is less than epsilon is not required to check of stalling the algorithm. Similarly, if the graph or surface of the function fx nearby the point xk is stiff, then the stalling condition does not require this. But as we do not priorly know whether this xk, the sequence of iterates generated by the algorithm, is going to move towards a flat or a steep portion of the graph of the function fx, we need to use these both the conditions, this condition and this condition, for identifying a stalling and hence a stopping condition for a general descent algorithm. However, we notice that both the conditions, these and these, are scale dependent. That means if we go for changing the variable space from x to some other space x hat, then this condition is dependent on the scaling of the variables, and this condition is dependent on the scaling of the function value. So what we do that have we ground to a hold is checked out by considering the relative change of the variable values is less than epsilon or the relative change of the function value is less than epsilon. These two conditions are checked to check have we ground to a hold. So here we simply replace these two conditions by, for this condition we replace it by checking the change of the value of the ith variable due to the movement from xk to xk plus 1, and consider the relative change, divide this quantity by maximum of absolute value of xik and a typical magnitude of xik. This quantity is less than epsilon for all I is equal to the n many components of the variable x. So this condition is replaced by these n many conditions, and this condition is replaced by, in the numerator, fxk plus 1 minus fxk divided by maximum of absolute value of fxk and typical magnitude of fxk is less than epsilon. Here again I would like to alert you that we should not deliberately replace this typical magnitude of xi by 1, and we should not deliberately replace this typical magnitude of fxk by 1. We should not do it. We also should not do replacement of this entire maximum of this quantity in the numerator just simply by 1 plus absolute value of xik. That eventually does not reflect the sense of this maximum of this quantity. If you don't consider a typical magnitude of xik here, then we notice that this quantity does not actually reflect a relative change of the function value, because this typical magnitude of xi eventually identifies the scaling factor of the variable value of xi. Unless this scaling factor is divided, we do not get this quantity as a relative change of the variable xi. Similar is the case that here we should not deliberately replace this numerator just by 1 plus absolute value of fx. So therefore, have we ground to a halt is answered by these two conditions, that you check either this condition is holding or this condition is holding. So accumulately, a practical stopping condition is you check whether out of the three conditions are satisfied. Those three conditions are these as the first condition, these as the second condition, and we have an answer to the first question, that have we solved the problem, that was answered here by this condition. So this is the third condition. So a practical stopping condition is that you terminate your algorithm if either of these three conditions are satisfied. The condition third is here. The condition 1 and 2 are written over here. Now I will end up this lecture mentioning a geometrical sense of why a flat graph of the function f is likely to satisfy this condition and a steep graph of the function f is likely to satisfy this condition. We notice that if we consider a steep graph of the function f, that is say steep around the point xk. So if we have here say the iterative point xk plus 1, and here is xk, then we notice that although by the movement from xk to xk plus 1, from this point to this point on the graph, the function value has substantially changed, but the difference between xk and xk plus 1 is substantially small. So for this such graph, this condition is very likely to satisfy, but we are yet to improve the function value, and then for such a graph we need to employ this condition as a stopping condition. However, for a graph of the function that is flat, let's suppose we have a graph of say this kind, then we see that for this graph the consecutive iterates xk plus 1 and xk, they are far away, but still the function values are very close at the point xk and xk plus 1. So for these such graphs, this condition is automatically satisfied. So for this such graph, we go for taking the stopping condition as this condition. With this visualization of graphs, let me stop the lecture here. In the next lecture, we shall start our real agenda of the entire course, that algorithms or methods for optimization problems. In the next lecture, we shall consider to discuss about the steepest descent method, one of the commonly used optimization algorithm to solve unconstrained optimization problems. Thank you all for all of your kind attention.